Most of the time you're most of the time you're running jobs in what we call the batch mode, but often you want to get in and interact with um, your application directly. So we'll talk about what that means and try and give you a feel for what that how that would work for you. So this is part of the complex project. Complex stands for comprehensive learning for end users to effectively utilize cyber infrastructure. So it's a specialized program where we're trying to give people the general non-programming skills that you would need to run on HPC systems. We know that it's a challenging environment. It's different, unlike anything you've been on before. And often you're there using HPC systems because you need to. So we're doing our best to give you the skills and introduce you to the technologies that you'll need to be successful in running your applications. So this is an outline. We'll talk about what's interactive HPC. Then we'll talk about accessing the interactive nodes, and then examples of interactive applications, and end it with some questions and answers if you have them. So you can do amazing things on supercomputers. Typically, what's run on there is very parallel and very large memory. And these are high-end computations for anything from tracing fish migration to solar flares to um, uh, high energy, high-end solenoids to tracking the planets to biological or genome studies. It's massively different. During COVID, our systems were used as part of an emergency disaster response mode to compute new drug mechanisms, and Paxlovid came from some of that work done across the nation. So supercomputers are very beneficial to society and the researchers doing applications for society. So we're really proud of it, and we do our best to keep things running for you. But you have to run your jobs on HPC clusters. So these are very powerful, as I said, but they are complicated. You can run jobs from the command line. So when you open up your laptop and you have a terminal and you're typing into that terminal app, that's what we call the command line interface. On the system, you can run jobs using the batch queue system where you put a request together, drop it into the queue, forget it, go get some coffee, come back, your job is done. Or there's application clients like PyTorch, TensorFlow. A lot of you working with machine learning would recognize those. So there's different ways that you can run your jobs on these big systems. Jobs scaling from one core to thousands to tens of thousands of nodes, depending on what system you're in. So they're all different scales and different memories as well. And for the larger jobs, schedulers are used to coordinate. This little cartoon shows a person at a terminal, like a laptop or this, an old-fashioned terminal in this image. You log into what we call the login node, which is where you can access your files. And behind that are the compute nodes, but you can't get directly onto them easily. You have to have a plan, you have to go through some scheduler, and we'll talk about that. And then your jobs will be coordinated and run. You wouldn't know which of these thousands of nodes to run on, but we have schedulers that help you pick that. And we have complex topics that cover a lot of this material separately from what I'm talking about today, the interactive computing. Oh, and you also will need to store data. Everybody's got lots of data these days, and it keeps growing. So for Expanse, we have an interesting architecture which is scalable in and of itself. We have behind over here is a picture of a rack. If you've never seen a computer rack, they tend to be very tall, 7 feet tall, maybe taller. And they have all this hardware that's put in slots, and they're linear and they're interconnected. And here the company that Dell put the system together, and they light up the cooling system for Expanse. And we keep adding more and more racks to Expanse. A unique feature of Expanse is every rack has what you need to run most of the jobs that Expanse are designed for. So you have CPUs, GPUs, and some storage right on each rack. Bigger jobs will run in an interconnected mode between these different racks. So this picture shows that we have 14 chassis, but I think we're up to 17 or more. We have high performance storage. a Lustre file system that at the time this slide was made was 12 petabytes, but I think we have more. And we have object storage using Ceph and a high-speed network. So we're connected to the SDSU high-speed network, more than a gigabit per second now, connecting out to the high-performance computing universe, Scenic, Exceed, or now Access, Amazon. You can connect to anything out on the cloud. So it's a very powerful system that we're continually updating. And there is a link to the machine, which also has a link to a user guide that always has the latest information. So talking about supercomputing jobs, HPC jobs, they can be run as what we call a batch job in the background or interactively, real time. And we'll learn about that today and distinguish it. This one shows a person sitting, again, at their laptop or a terminal with a keyboard attached and a computer behind it, trying to run a job on the HPC compute nodes. So you submit your jobs to the batch queuing system. So when you submit your job, you just submit and come back later. And if assuming everything's written correctly, the job runs and you come back and your data's done in a few hours, a day, a few days on expanse, maybe longer, and you'd get some special permission to do that. We also have portals for application interfaces. The portal is a way to access Expanse without having to log in, remember where you are on the system. The portal has applications that you can run, and we'll talk about that at the end of the day. MATLAB and other, you can launch a Jupyter notebook through the portal. You can even access a command line terminal through a Jupyter notebook type of application. And so we do support all kinds of Jupyter applications using the Galileo application, which I'll talk about in a moment. We don't support Jupyter Lab, we support Jupyter Notebooks and Jupyter Lab, but we don't have the larger Jupyter Community app. So that's based, and so high performance computing are large jobs with large memory that will run for a long time, requiring specialized programming languages. And next we'll talk about these batch jobs that I've been mentioning. So what's a batch job? Again, it's any HPC or HTC high throughput computing system that's usually going to use a cluster of machines, and you need to be able to share these computational resources fairly between users. And without that sharing, there would be some kind of anarchy. So the job of the scheduler is to look at all the people trying to use the system at the moment and read a job descriptor file called a batch script, and uses that information to schedule intelligently all the different kinds of jobs. So sometimes you might wait 5 minutes to get some jobs submitted, or you have to wait an hour, or it could be even longer if there's a large number of jobs in there. But the schedulers are fair as can possibly be made. And we just call them batch systems. We use a particular one called Slurm. I'll talk about that in a moment. These batch systems, wherever you are across the Access universe, the US high-scale compute system infrastructure, there's going to be similar kind of batch queuing system. So there's a scheduler, again, that takes your input and figures out when your job should, could, and can run. And then there's different queues that you could submit to. And the queues might have policies on them, like a limit. There's a debug queue is 30 minutes, and the regular queues are 2 days. So, and there's different kinds with memory. You want high memory queue. You'll be able to make some different choices, a CPU queue, a GPU queue. There's all kinds, and we have all of that is in our user guide. I won't cover that in detail today, but we have complex webinars on those topics, and we also have it all in the user guide. And so there's different queues that you can try to use. And then the queues, everything is partitioned. These jobs are also the queues are also partitioned. So the queue can be configured for different kinds of jobs. So you'll need a basic understanding of how batch jobs work. And again, we have a complex webinar coming up on that, and some recorded ones for you to go look at. It just would help you understand why things might take longer than you expect, and also to write a correct description, you have to write a script that will describe what you need. So the main goals of the scheduler are to minimize time between job submission and completion. We don't want our queues our hardware to be idle. And a job should not stay in the queue for a long time either. We need to optimize the use of our CPUs. The algorithms focus on minimizing that. They want to maximize job throughput, get as many jobs done per unit time as possible, and run the jobs automatically in the background. And then when the job is done, a really important part of this batch queue is to finalize your job. Ensure it finishes and that the results are recorded and stored where you want them. And all of that information is in that batch script. And so simple batch schedule, we'll talk a little bit about that. As a user submitting jobs and they log into the front end node, you create a shell script batch with particular keywords in it that notify the scheduler that it's a scheduling script. It's basic Unix, Linux type of script, terminology and environment variables, all of that is in the script. And then you submit that to the job queue and they get submitted and then evaluated and assessed by the scheduler. And then the job will be launched to run in the system when it's the right time. And we'll talk about that just briefly in a moment. So you don't, with a batch scheduler, you submit the job, you don't run anything interactively with the batch queuing jobs. You're going to be non-interactive, with a caveat to that when we go to look at the interactive jobs scheduling system. And they are all about the same. All the schedulers work about the same. They're open source. Some cost a lot of money. You can imagine on a system like Expanse, if you get high quality system schedulers, you're going to pay something for that. So we use the Slurm Resource Manager, the simple Linux utility resource management. And if you're a Futurama fan, yes, they did use Slurm on purpose. So they used to give out little cans of this green colored gooey drink at meetings called Slurm. It was pretty bad. I had a can of it for a long time, and then I think it kind of exploded a little bit. So anyway, Slurm is open source. It can run on many systems. If you want more features, you pay for that. And it's sort of like what we call the glue. This is another version of that cartoon I showed you of a user logging in, working on their home system on Expanse, for example. Then they decide to submit a job to schedulers in its own server. And it's like a gate. You can't get past onto these machines without going through the Slurm scheduler and getting permission to run a job. And in the background, Slurm will launch and run the job for you. But you can ask for an internet interactive connection, which is what we'll talk about today. And then all the computing nodes are in the back and they'll do their jobs. And when done, the Slurm system will grab all your data and put it where you ask it, return information about the job to you. So its role is to allocate these resources. This is the client architecture here. Here's all these commands that you'll learn to run, to submit jobs, to check what jobs are running in the system. And you talk and interact with controller daemons. Obviously, this is not going to be just one application. Slurm is a collection of interactive management systems. And if you want to know more about it, go to the slurmschedulemd.com and learn about Slurm. So how does it work? I love this multi-dimensional Tetris term. So here you have some jobs that are running across multiple nodes, 6 nodes. Some jobs are one node jobs and some jobs are multi-node jobs. And the order in which they were submitted doesn't matter. What happens is around the same time, 9 jobs got submitted by different users. And the scheduler decided to start running job 9 and then job 2 in the multi-node model. And then 6 and 1 got fit in and start when job 9's over. Job 3 is a longer running, it's just on one node, but then jobs 4, 5, 7, and 8 are then submitted at different times on the same node. So again, job 5 might have been submitted before job 9, but the best fit for the system was to get to run it later on because it's so short. It's done pretty quickly, but the way the scheduler works, you just have to trust it. Now, if you submit a job and it's in the queue for 2 days, there's something wrong and you should reach out to the help desk people. By the way, we've got Nicole and Marty here to answer questions. They're part of the complex project and part of our user support group. And all day long, they answer these questions. And I usually say it several times in my talk. If things aren't working and they normally did, reach out to the help desk, because when things normally run and you haven't made any big changes, there could be something going on. Like today, there's a little problem with the luster system. So it just depends, but be sure to get to know our support people. They're very helpful, and they'll answer any questions that you have. I can't really see the chat, but they'll be watching the chat for any questions you've got. And so there's all kinds of things done by the scheduler and all kinds of parameters that affect the scheduling. And in your batch script, you'll define some of these parameters. There's probably 23 or 20 or more keywords you can use to define, like how much memory you need, how many cores you want, how many nodes you want, how long you expect it to run. You do need to define a few. And again, in our batch scheduler webinar, we go through all those details, but everything you put in that batch script affects the scheduler's decisions. And the first thing it checks for is to make sure the syntax is right. Is the syntax correct? Otherwise, you'll get it rejected pretty quickly, and you'll have to figure out and debug it. All right, so what's the difference then between batch computing and interactive? For batch computing, you still had to log on to the node. You had to test and maybe do some compiling, maybe update your batch script and decide where your files will go. But once you submit it to the batch in the batch computing mode, you wait for it to be done, and you can monitor the queuing system. Interactive is when you're interacting with your computer. My favorite example is right now we're all doing, in computer science, interactive computing. We're all using software on our laptops to watch and monitor and see my talk. And at the same time, you've got multiple windows in there. You've probably got your email client there. You've probably got Word running and PowerPoint, a couple of terminal shells open. You might be even running a local version through Anaconda of a Jupyter notebook. There's a lot that you're doing on your laptop. And just from the computer science perspective, that's interactive computing. But interactive high performance computing is something done on a high performance computing resource, like a high-end compute node. Back in that image I showed you of the user with all the systems back behind it, those are the HPC nodes. They're not normal, they're not accessed or used typically. They do have Linux running on them, but they're very specialized and customized. They're very expensive. So if you get access to one, and you're allowed to do that for all kinds of reasons, then you log on to that node, or your application is running on that node, and you own it, and nobody else, no other application is running on that node. And so you can get really good scaling in your analysis or running something. And examples are PyTorch or running Jupyter notebooks. There's all kinds of things you can be doing real time, interacting with your HPC computing application. So you can use it for code development. You're not supposed to run any kind of code on the login nodes. So if you're testing and debugging something, MPI app or a Python app, a parallel app, you can develop it on that interactive node. And you can do real-time data exploration with parallel applications and visualize your data. And it's typically used when you have large data sets and are too large to download. If you're putting out a petabyte of data, or even a half a terabyte, or a few hundred gigs, it takes a long time to move that data, and it won't fit on your laptop. Whoops, sorry about that. Whoops. Somehow my back button's not. So I don't know why I'm going in the wrong direction here, folks. All right. All right, when would you need to use an interactive node? If you're using something that requires interactive with a lot of data, like MATLAB and notebooks, or you need to stage a large amount of data. AI applications, or you need to compile something very large and complex. There are applications that can take 30 minutes or an hour or 2 hours to compile, and sometimes those are even done as batch jobs. Okay, so I'm really having a problem navigating here. I think I'm not happy about this. Yeah, I skipped over a couple of slides. My apologies. Let's go to this one. For some reason, when I hit my up and down arrow keys, they're not being recognized. So examples, like I said, of HPC computing applications that would run on an interactive node would be a Jupyter notebook. A lot of us are using Jupyter all day long, and we don't want them running on the login node. There's too much else going on the login node. So we want you to ask for an interactive node to run your notebooks. MATLAB is very popular. There's a parallel version of MATLAB that we support, and you can run it. And I'll talk about using that through our portal as opposed to trying to launch it yourself. And then Jupyter, parallel Jupyter running. This is an example on the Lawrence Berkeley, the NERSC Cori system, where you can get multiple cores in the back end to run your Jupyter notebook. And then ParaView is a very popular HPC application. So we have something called the Expanse portal, and you can log on to the portal. We'll try to get to examples of that towards the end of this talk, depending on how things go. But the portal you log in using your portal ID and your authentication, your CI login authentication, for example. And then you can create a Jupyter notebook. You can run, this is an example of launching a notebook. You can run MATLAB or Studio, and you would use it using your Access portal account. And this is an example of the Jupyter notebook. And one of the things I always like to point out is when you get a link to a Jupyter notebook, the URL is actually a password to the system. If anybody gets that, they can get right on and start running things on the computer. So don't leave it in a vulnerable area open. Be sure to lock your screen, but be very, very careful. Use secure connections and use the portal is what we recommend. All right, so how do we access these nodes? There's a couple of ways to do it. Why would you need to use it? Again, I said this when your applications are large and you would need to access large amounts of data, or you just want to run an application like MATLAB or notebooks, use the portal for those. When you want to run AI applications, those are not allowed to run on the login node. You might get away with launching it, but if the sysadmin people see it, they'll kill the job. Again, there's just not enough resources for people to be running PyTorch, or you need to compile large scale applications. Okay, so to get an interactive node, you use the special command. It's called the srun command. And here, these are pulled. I tested them last night. They both worked. So I know everything that you need to know is in here except your account, which is that user account project account that you would have on Expanse. So this one is for CPU and this one is for GPU. They're also in the Expanse user guide. There's always updated and correct CPU, GPU. So if you try this, it doesn't work, go to the user guide. My slides could get out of sync with updated material. So try checking the user guide if these don't work for you. That test data is old. I tested them last night. So you wanted to find the partition. This is the debug with the maximum wall clock time of 30 minutes. And you need to give the account, and then you want to put the number of tasks per node. I don't know why it's telling me this. Sorry about that. All right, so let's look at getting an interactive CPU node. We have a README file in the GitHub repo associated with this these examples, and you can also look in the README file. The idea is you can cut and paste this, make sure you use the right account number, You're going to want to set up the right module environment. If you don't know what modules are, we have a webinar for that. But modules are a way of setting up a customized environment for exactly what you need to run exactly that particular application. And here we're just going to use MPI run 16 cores, and we're going to run MPI prime. And it goes through some default runtime, and we get prime numbers in that example. This is for GPU now. And so we're asking for the GPU debug. Everything else is pretty similar with how many tasks per node, how many nodes we need, the memory, one GPU, 30 minutes because we're using the debug partition. And in this example, I don't run a code, I just show you. You want to know, am I really on a GPU? And if you run NVIDIA SMI, you should find out that you've got NVIDIA GPU going. This brings back information. And also notice I was on the login node, and now I'm on this node, the Expanse -1457 node. So I've gotten my interactive node, and now it's sitting there, and I have it for 30 minutes to do whatever testing I need to do. Again, there's other ways to run applications, and a common one is X11 forwarding, but we've discovered that X11 is not as supported like from a Mac system. I don't have Windows, but you guys can try it. I just wouldn't recommend it. I recommend you use the portal for these visual applications that you're trying to use. But for X11, I'm sitting on my laptop with a keyboard. I'm using it right now, but the application I'm using it is taking care of all the X11 details. There's a server, there's a client, and through the network, I talk to an X11 client on the remote machine. And if you want to know more about that, it's just a interesting thing to know that there's applications that are connecting you to the remote systems like this. On Mac OS, you can do your own forwarding if you have a custom application. It's just very challenging. So you want to connect using the -Y. This allows you to run a remote visual application. And so if you have Brew, you would install it that way. What you need to have access on an interactive node where you can launch an application, you really need two windows. One is the first window, you request your node, and I get logged on to Expanse -955. In window 2, I log on to Expanse, and then I log on to my interactive node. And now I'm logged on in a terminal mode, and I can do things that I need to do on that node as well, including I'm going to try and run MATLAB. Okay, and the MATLAB it's really challenging. I recommend that you go to the portal and use the portal, but in case you have to do something like this for a different application, I'm showing you what happens. So it depends on your local host X11, and GNU+'s a pretty old code. It's been around for a long time. It's designed for visual display of data. So you run your code, data gets stored in the directory, and you try to plot it with GNU plot. It's very powerful. You can do a lot with it. But again, because the X11 forwarding is a little bit of a challenge, it doesn't always work so well. But here I'm loading in the modules for GNU plot. We support it. And I know I've got it because I do which GNU plot it's there. And then I run GNU plot, and I'm inside GNU plot, and I set the terminal to xterm, and I try to plot the sinusoidal wave function. This is an example of what things look like when they go right. But on Expanse right now, all I get are black and white. So again, you could use it if you have old code that uses GNU plot, but I suggest you change to something different. Now we're going to move into the part of the talk where we go over some actual examples for viewing data. Then we'll look at programming and platforms and gateways and portals. So to view data, there's different data formats, and some of them are what we call a binary data. Many of you probably store your data in what we call ASCII. It's like a .text file. You can read it if you just do a cat, myfile.txt. But if they're in binary form, it's compressed data with information associated with the data. And NetCDF and HPF are two different. There's a couple different kinds of data formats that are used, like NetCDF has evolved from the climate modeling community. The other one is high density format. Both are supported on Expanse, and they've been updated. But you have clients that like an application that will allow you to view the data. And when it prints out, you can see keywords, characteristics of the data, and also it prints out the data you're asking to see. So it's very complicated, and you may have inherited an application where you're working with it. So getting it set up is not done by default, but you can work with the help desk people to help you analyze and view your data. So just going through, this is a very simple SciNet from Canada example that I download, and it's available in our training modules. So you have to set up these modules. You have to put the environment variables into your batch script. You have to compile your code. The example will generate a data.nc is their file extension, and you can browse and query the data. So again, you need to load all the modules. So the first thing you might do is module spider netcdf. There's all kinds of versions that are needed, that are available, and all kinds of combinations of which of the CPUs, the compilers, and the MPI that you want to use. I found a simple one that worked, but if you're having trouble and you need to do this, reach out to the help desk. So I'm listing the modules I've got. I add in the ones I need to run netcdf, including a netcdf-c/4.7.4. I make sure they're in there, and then I look at my bash profile, and I'm showing you the different 4 variables that must be set for the netcdf to run properly, and the paths are in there properly. So now we're all set up, and we have the link is at the end of the talk. We have a GitHub repo of HPC training examples, and one of them is a netcdf. I've got a folder of those examples, and here I have something called 2darray.c. I compile it. This is you have to have libraries that are included, and then you can compile this. So sometimes this can be tricky, and this example works for me when I set up my environment variables correctly. So now I've run it, and I look for an output data file, and now I can query the data. So if you just do an nc dump, that's the query command, -h, it'll tell you all kinds of arguments. And so I ask it to just give me, I just ask it to give me the data output for a very simple amount of data. So here you can see there's X and Y. It gives you the names of the variables, their definition, variable type, and then -X will give me XML output. And then here I'm just dumping actual data. And there's so much data I have to use, snip out. But you can see the real data. So it's a way for you to very quickly check your data. You can also use something called NCView and do an interactive visualization application. And that's where an interactive node is valuable. All right, so let's move to other platforms. How are we doing on time? Doing great. So if you want, you can run MATLAB from the command line, depending on the system you're on, but it's very painful. You can load in the libraries and get it to run. I have found for myself at the moment, because we still have this X11 issue, that it runs and does computational work, but there's no plotting. Nothing happens. And I'm told that it's because of the X11 problem, which is why we recommend you get to know the portal, because you can launch a full MATLAB or R application from the portal that's running on Expanse on an interactive node. But in case you want to do it, here's the details again, the two windows, and you have to log into 2 windows and get that interactive node, then log in over to the interactive node and run MATLAB. Again, use the Expanse portal if you can, and trying to use it, if it doesn't work the way you want, reach out to our help desk so we can make the portal better for you. That's the whole point of it. Again, I did get it to run on the portal, okay? And the plotting, this is just a simple example. This did run for me, but it took about 5 minutes, and fortunately, network connection was stable. the other thing about running an advanced application in an interactive mode on an interactive node is it's highly dependent on the bandwidth and the stability of your network. I live up in Encinitas, and for 20 years it was perfect, but now more people run other things like games and things like that. And I've noticed my network is way too unstable for me to run this kind of job. The portal maintains connections for you in the back end. It's what it's designed to do. So you'll feel like you have continuous connection. And you can run R on TSCC. For those of you who are TSCC users, it's very similar, it's just a lot easier because they have it supported on the system. Okay, so Jupyter Notebooks. We all now know what Jupyter is, but it's an open source interactive tool. And it's running in a web browser, so it's using the stability of a web browser infrastructure. Again, the browser is designed to make the connection appear to be continuous, even though it might have latency. It's all this stuff going on in the back end, and I think that's one of the reasons Jupyter notebooks are used, aside from the amazing fact that in a notebook you're inside your application. It's fantastic. You can go change variables. If you haven't used them, play with them. They're really fun. So there's common Jupyter services are the notebooks, Jupyter Lab, where you can run more notebooks, multiple notebooks at one time and open up a shell terminal, or a Jupyter Hub. We don't run Jupyter Hub for security reasons at SDSC. All right, so to run the notebook, there's a lot of ways you can run it, okay? And we support many ways. You can run a notebook locally install Anaconda on your laptop. But if you want to run remotely, the default for Anaconda is HTTP, which we don't recommend that and we don't support that. It needs to be HTTPS, so the connections are encrypted. But the default is HTTP. So you have to do a lot of work to get over that fact. You can connect over HTTP, but it's going to be insecure, and if you're trying to do it on the login node, we're going to kill that job. You can connect over HTTP plus SSH tunneling. It is secure, but it's inconvenient. And the main reason is you open up a port on your local laptop, you open up a port on the remote host, that could be a compute node, but you don't know how stable the compute node port is going to be. And how stable your network connection is. If your network connection goes unstable, you're most likely are going to lose that port connection on the interactive node you worked so hard to get. So it's there. We support it, but it's just like I said, it's inconvenient and not stable. What we've developed is a solution that we've found to be very useful. Internally, we have the satellite reverse proxy service that generates a secure URL connection using an application called the Galileo client. You use Galileo, pass the arguments to it, kind of like that srun command, and Galileo talks to the SRPS. They talk with the batch scheduling system for you in the background. They get you a node. They give you an immediate HTTPS URL connection. It's a wonky one, but you put that in the browser and you wait until the notebook is available. We get really good feedback on this approach, and I'll show you an example. But remember, treat that notebook URL like a password. So architecturally, what I'm talking about is here's another view, a lovely diagram made by Marty, who's one of your consultants today. You have this big system with all kinds of racks and all kinds of nodes on the racks. You've got network, and it has its own internal network. And because it's behind the login node firewall in many firewalls, it just has to be HTTP internally. Somewhere there, we're going to launch a Jupyter service, and we've got the SRPS as part of the satellite reverse proxy service. It's this service that will help us get a node, get an HTTPS connection to whatever node we get. So again, it's all interacting with that batch queuing system, but you didn't have to write that. You just used a simple command from Galileo with a few arguments. So you log on via SSH, so you're securely connected to the login node. You set up your Galileo command, you run that in the background, then you'll get back an HTTPS link. You put that in your web browser, then you just wait. And it's also done on purpose with a weird, wonky token and several wonky words to make it really hard to guess. And it's very secure, and we trust it, and we hope you'll trust it too. And you can run Jupyter Lab or just a Jupyter notebook behind it, but not Jupyter Hub. All right, so again, this is in a little more detail of SRPS, and I don't really need to spend a lot of time on that. But I want to show you how Galileo looks and works. So you have to make sure you have Galileo in the path. So if you don't want to mess with your .bash underscore profile file on Expanse, here's the path. And I'll give you a link to the Galileo project page where you can also cut and paste directly these commands. And then you can look at all the arguments for Galileo, your account, your reservation, other information. And I apologize, somehow that went forward on me and my backward's not working. So here we go. We log on. Which Galileo? No Galileo. Oh dear, I need to export the path. Which Galileo? Now I see Galileo. I can launch it. You have to remember to change ABC123 to a real account number. I want the shared partition, 2 CPUs, 4 gigs, 30 minutes. And one thing important is to, for the environment, for modules, you want to make sure you get the right CPU and Anaconda, for example, here, and then submit it. Submitted Jupyter launch script to Slurm. Your Slurm job ID is this number. You can go into another window and monitor that job ID to find out how long is it going to take. But what you get right away is you get this secure HTTPS connection. You don't have to wait for that. You can take this and remember to copy it, because once the terminal screen is closed or anything, you have to record this yourselves. So I usually put it in a side file. But you can put that into a web browser and then watch the status of your notebook request. You can run SQ on that job partition to see pending, and then sometime later the job is running. So you can also be, looking in 2 places. Sometimes it can take a long time, and you might think, oh, is this timed out? No, you can look in here and see, oh no, my job is still waiting. Things are just really busy. And then here's that status pending page. In the queue running mapped, that means it's mapped, but we're still waiting for something. And then once it's proxied, up will come your web browser. So again, it may take a while if the job queue is busy. And again, treat that notebook URL as a password. It literally gets people into your account. Can't say that enough. And again, here's that job. You can see it's running. And now what does it all look like? Putting it all together, there's Galileo with its options. You run the Galileo command, we get some status, and up will come whatever I tell it to start out with. You can navigate through a folder and subfolders. And again, I'm pointing to our Expanse notebook collection, which has a lot of notebooks that we try and test every year that you can use for like starting. It's good to have a hello world. My philosophy is if hello world works, a lot of things have come together. If hello world works every time except today, when I'm doing this same Galileo command, there's probably not your fault, and you might reach out to the support group unless you made a change to hello world. Okay, and then here's the detailed text version. Here's the Galileo launch command again. Don't use that. You're not in use 300. The partition. And then here we're running with a container. That's the best way to do things, is find a Singularity Pro container. And Marty works really hard in the team to develop a lot of containers in CM shared apps containers. If you want an idea of the scope of all the libraries and applications and data that our team has to support, maintain, and keep running, just go to CM Shared. It's massive. There's hundreds and hundreds of libraries and sub-libraries all connected correctly. And anyway, go in here. There's all kinds of containers you can use, like you want to run PyTorch. And then submit. And here's another URL, a wonky one. And again, another job ID. So this just expands out the example. And this one is for GPU submission. So you can use Galileo to get CPU or GPU. And here's an example of a notebook launched on a GPU. And again, you just run NVIDIA SMI. And it's like I said, this is like the hello world of getting a GPU node. You want to make sure your main approach to running code is working, and then you can have more complicated notebooks. But when things don't work on your new stuff, go back to the basic hello world. Okay, so the Expanse notebook example is in this URL, and again, I think it's in the references section. And we have a large number of different kinds for GPU parallel, GPU, CPU serial, and we try to tell you what Python packages are required. Most of these are Python. All right, and gateways and portals. So this is our Expanse user portal. And if you're hanging around and you want to ask a question, one thing I'd like to do is make sure you can get on the portal. And again, it allows you to navigate through, look at your files on Expanse, and it has notebooks. It supports MATLAB. It supports R. I know there's an R community that uses Expanse, and R is very complicated, but we have full support. The portal is based on software made by the Ohio Supercomputing Center, and they keep it well updated, and they do a good job with the apps that they do support, which is why we're working with it. You can get a window, a terminal shell, things like that. And you would authenticate using your access, like your CI login credentials. If you still need to make those, go ahead and start applying. Anybody can apply who's from the US. There are some conditions. You have to have a US location. Okay, so, and everything is secure. So everything is HTTPS, SSH in the back end. And the beauty of this is maintaining that network connection. So if you're going to ask for a node for 10 hours to run your complex MATLAB application, that network connection, as much as possible, will remain stable. And I think it will track if things go bad. There's always that time when the whole network in the entire country goes down. But for the most part, your network connections will be stable. All right, and then again, file management. And here I'm showing the open on demand portal view, the portal view into your files. But over here, if you were just using the terminal, that's what my files look like as well. So it's two different views. It's depending on what you like. You can always manage your files here and the portal would reflect it, or you can manage your files on the portal. You can build jobs, like this one is a job request. If you want to run MATLAB or R or even a Jupyter notebook, you have to build up a request and submit it, because in the back end, it's still negotiating with the Slurm manager to get you an interactive node to run your code. So it might take some time. So keep an eye on the SQ for jobs that you have queued up. And then here is launching the notebook. That we have a example in here. This is a default notebook launcher. Everything in here except the account, you would have to modify that, but you can literally take all these values and put them in. And they worked for me yesterday to launch a Jupyter lab. And the other ones that are not there, maybe you're not doing your own Conda environment, but we do support that, and we have a training video on that. But this should be enough for you to launch a notebook on Expanse. All right, and that's the end of my talk. Any questions? Thank you for listening.